So when we stopped last time, we'd been talking about the branches of the immune system and how we had the first line of defense, which was barriers. So we had been talking about stuff like intact skin, mucus, flushing mechanisms. And then on this slide, we had talked about some chemical barriers to infection. And so what differentiates these from the mechanical barriers is there is some kind of chemical nature to these that helps destroy or slow down microbes. So things that have antimicrobial properties, acidity in the skin or the stomach, digestive enzymes in the stomach, acidity again in the vagina, and then some antiviral chemicals called interferons. So these things, these chemical barriers, if we look back at how the immune system is structured, they're actually falling under the second line of defense. So you might want to make a note right before that slide that chemical barriers, including those chemicals that we talked about, that's second line of defense. And there are some other factors that are part of the second line of defense that still fall under innate immunity. So the type that you're born with, the type that acts really fast, it's kind of weak. You don't have to have seen the pathogen before. So first line of defense and second line of defense, that's still innate immunity. The third line of defense, that's called acquired immunity, and I'll come back to that in a few minutes. But I want to talk about next some other mechanisms that our body has to help protect us from pathogens, which are not exactly the same as the chemicals. And the first one of those is inflammation. So inflammation is a process. It's not a chemical. It's not based in a particular organ, but it's a process. And it does not feel good to have inflammation, but it serves a purpose for the body because it's trying to protect us from harmful pathogens or harmful substances and help get rid of them. So I do want you to know what are the signs of inflammation, and these will sometimes be called the cardinal signs of inflammation. And this picture is showing them and sometimes giving them their Latin name, which is really old school. These are their current names. So any part of your body that is experiencing inflammation will have most of these signs. It will turn red. It will swell up somewhat. It might feel hot if it's in a place where you can feel it, if it's on the outside of your body. It may hurt, and you may somewhat lose function in that body area. Those are the signs of inflammation, and that's something I want you to have memorized. And it's easy to, they're always showing the picture of you prick your finger, the stuff that happens to your finger, that is the signs of inflammation. Red hot, swells up, hurts, and you might not be able to use it as well. That's inflammation. So all of those things that happen during inflammation, they're happening because your body is trying to help you fight off a possible invader that is causing a problem. So this part of the lecture, I'm going to go through it a little bit faster and also write some extra notes on the board over there, but this is what actually is going on in the inflammatory response. And these need a little bit of introduction. So what these pictures are showing is a nail puncture, like a nail that you step on, or probably you would step on. I don't know why you would jab it in like this, but something puncturing the body through the skin, and it's also bringing in bacteria from the outside. So that's a situation that our body would detect as a problem and then start this inflammatory response. So the first thing that happens is you have these immune cells waiting under the skin, and they detect a problem, and they start sending out these inflammatory chemicals called cytokines, and that's part of what comes out of the granules in white blood cells, is these signaling inflammatory chemicals that are kicking off this process. Other details of this you don't so much need to know for this class. But when those chemicals enter the bloodstream, they cause the blood vessels to dilate. Again, something happening with blood vessels. They're now dilating and they're becoming more leaky. So those same little slits and capillaries that we talked about before, they're bigger now. Fluid can come out. That's part of what gives you swelling. So you'll have fluid coming out, and you also have white blood cells squeezing out of the blood through those cracks and coming into this area to fight the infection. So at this point, we've got the following things going on in inflammation. We've got inflammatory chemicals, blood vessel dilation, which is making them more leaky. We get fluid and white blood cells in the area of the inflammatory process. This part causes the swelling. You've got more fluid going into that area. You'll have temporary edema out here. You've got white blood cells trying to fight against bacteria, hopefully killing some of them. You might have pus, which is dead white blood cells and debris and fluid. That also can add to the swelling. And this part, just the blood vessels on their own dilating, that gives you the redness and the heat, because you've got more blood flow to the area. And there's a lot more detail going on here, but you've got a battle between white blood cells, bacteria, stuff is leaking out, more blood to the area. That all gives you the inflammatory response, and it's supposed to be helping you fight off foreign invaders. And then this slide is showing, as that battle continues, you have pus formation, more edema. Gradually, this will also get cleaned up as it heals, but that's the inflammatory response. So what I want you to know for this class are, what are the 5 signs? Memorize that. And kind of at a multiple choice level, be able to recognize, where do they come from? How do they end up that way, in a real general way? Questions so far? The details of that are one of my favorite things to talk about it, but we don't have time in here. So, inflammation is a process. It's part of our protective defenses in the second line of defense. It's part of innate immunity. And another protective mechanism that we have that's part of the second line of defense is phagocytosis. So it kind of goes along with inflammation, but it's technically a separate process. And this generally comes from macrophages. If that word sounds familiar, it's because those monocytes that we learned about earlier, particular white blood cells, how do you recognize them? Bean-shaped nucleus, real big cell. Yeah. They can eventually turn into macrophages. And the macrophages operate out here in the tissues, and they eat and digest debris, invaders, and so on. And they do phago, eat, cytosis cell. They eat cells. They eat bacterial cells very often. So they engulf and then destroy certain pathogens, especially bacteria. So you have these roaming around in your body in various areas to search and destroy and to literally eat up and digest bacteria. So that's a protective mechanism as well. The next one is fever. And this is something else that we tend to view it as a problem. Actually, fever helps protect you as well. So when we have a fever, it's actually initiated by our temperature centers in the brain, partly from those cytokines, inflammatory chemicals that got released back here. One of the things that some of those can do is signal the brain, we have a problem, please make it hotter in this area. And so if our temperature starts rising, we call that fever. There's a growing sense in the medical community now that we should, if people have a mild fever, we should leave it alone because it's going to help the person. Except in babies. Babies, we don't want to tolerate fever as much. But during fever, there are two helpful things that happen in our bodies. So we have macrophages that are eating debris and eating bacteria. They get more efficient and they work a little bit faster when it's hotter. And the second thing that happens during fever is that our body holds on to iron. We don't have as much iron circulating. And that may seem a weird way to protect us, but we hold on to it tighter and then there's less for pathogens to use. And as long as our body stays slightly hotter than our set temperature, pathogens will have less iron and macrophages eat things faster and that helps protect us. So a little bit of fever can be good. What's dangerous about having really high fever? It could kill your own cells. How? How's that work? They do get too hot. It's because our proteins will start to lose their shape. I may have heard somebody whisper that. Denature. Our proteins don't hold their shape well if it gets too hot. They start to denature.
What's too hot?
What is too hot? What's like super? What's a survivable fever?
102, 101.
Above 106, it's getting really dire.
Yeah, it's not 103. 101.
103, we start treating it. 106, 107 when we really
101.
start to cause that.
100. I don't know.
It won't denature proteins.
I don't know. You said, I said yeah. Like what?
106 or 107 is when it's too hot.
Oh.
Really too hot, yeah. Where we start to actually denature proteins. So at that point, might as well draw that on here. So there are some people that walk around and their temperature is a little bit less than 98.6. So I'm going to put 97 for the start point. So between 97 up to around 106, as you go up in fever, this is happening more, this is happening more. And generally being helpful, it will make you feel awful. But once you get 106, 107, it's actually starting to damage you. So we don't want to wait until it gets to that point to start treating it because you don't know how much higher it will go. But if you're a grown-up and you're generally healthy and your fever is 101, it might be more helpful than harmful. Probably. And then I think the last thing I want to mention in this segment about Second line of defense, innate immunity, helpful factors that your body has is something called natural killer cells, or NK cells. These are cells that you have, they're white blood cells, and their job is to recognize your cells that are a problem. So if something is going wrong with your own cells that's dangerous, natural killer cells can recognize those and try to kill them. That's why they're called natural killer. So times that could happen is if some of your cells become cancerous, it could be that your own body will destroy those before they become a further problem. Natural killer cells could do that. Sometimes cancer cells can't be recognized by them though. Doesn't always work. If you have cells that are showing virus infection on the outside, natural killer cells can destroy those too. Mechanisms are very cool. You just have time to say what they're called and what they do. But they're part of the second line of defense. So this chart has a lot of words on it, but all of these are sort of summarizing what are your innate immunity toolkit that you have in your body to help protect you. This one I didn't talk about so much, but we've got mechanical barriers, chemical barriers, NK cells, inflammation, phagocytosis, and fever. This goes with innate immunity. Where would you draw on here a line where first line of defense ends and second starts? Right after mechanical barriers. So above that, that's first line of defense. This is all second line of defense. And before I switch slide sets, I also want to review this one. So everything I've talked about with immune system so far, it's been innate immunity, first and second line of defense. And it has these characteristics. So these things could protect us from an alien microbe that's never been on Earth before. We've never seen it. We never have to have seen it. It would give us some weak protection that acts quickly and it's always with us. All of the things I've talked about so far. The part that I'm going to talk about next is the acquired immune system. And I tried to make the slide that goes with this similar to the other one. So this slide and the one I just showed about innate immunity, those would be especially good to study and kind of compare, contrast. And before I get into that, if our body is using acquired immunity, so this part, the third line of defense, this is acquired immunity. And if we're getting to that point, it's because pathogens have gotten past mechanical barriers. They've survived the chemical barriers. They've hidden or outrun natural killer cells. Inflammation didn't work. Phagocytosis and fever didn't work. Then we start activating our third line of defense, or acquired immunity. That's this. And for acquired immunity, you're not born with it. That's why it's called acquired. You have to develop it. And we have to develop it after we've come in contact with that bacteria, that virus, that pathogen. We have to develop it. It develops kind of slowly, so that's contrasted from innate. It's always present. This develops slowly, but once it does, it's a strong defense. It works much better. Also, once we have developed this, once we have acquired immunity to some specific pathogen, it lasts for years. So when you came to King, I know you had to provide a record that, yeah, I got vaccinated against polio and measles, mumps, rubella. If you did, you've still got immunity to it. It lasts for years. Sometimes up until you're 80. Sometimes you may need a booster, but it lasts for years because we have immunological memory. And this line of defense is majorly involved with antibodies, like we talked about with blood typing, and also B and T lymphocytes. The details of it, I'm not going to talk about too much, but you should connect antibodies and B and T lymphocytes with acquired immunity, with the third line of defense. So kind of a review. If there's a pathogen that gets into us and it gets past physical barriers, and it makes it past chemical barriers, and it survives the fever, and it doesn't get eaten by macrophages, okay, so it's in us. And the way our body recognizes it is by what antigens, shapes it's got on its surface. We recognize its surface shapes. So if it's a bacterium, like this oval, it's got shapes on its surface that we could recognize with antibodies. Here's another bacterium shown smaller. If it's a virus, it's got shapes on its surface that we could recognize by using antibodies. So it's the shapes on the surface of that pathogen that we recognize, and we use antibodies to do it. This is the same picture we saw back in red blood cells. This is antibodies. They have binding sites that can bind onto molecules, antigens. And remember that an antibody binding onto an antigen, you can assume that that's going to end in destruction. It can end in destruction. What kind of destruction happens if what this antibody binds is a red blood cell? What happens?
Whole cell. Or just for cell or something. I don't know.
The cell would die.
Hemostasis.
Hemostasis. Hemolysis is the word that you want. First, the red blood cells would clump because the antibodies are grabbing them, and then they would burst. That's hemolysis. And then you would probably die. If it's your own red blood cells. So,
I'm in. Yeah.
or the cells would die. Might also cause you to die. So imagine that process if what is being grabbed isn't blood antigens, but a pathogen antigen. You could get some of the same processes. So if a bacterium gets into our body and we can make antibodies against it, they grab on, they can cause it to be destroyed, they can cause it to be engulfed more easily, but the end result is going to be destruction. Getting rid of that pathogen out of the body. But it takes antibodies to do that. So if we're going to have a good acquired immune response, what we actually have to acquire is antibodies. So this is how that process generally would work. Our body would see the pathogen antigen, detect a shape, then we could make antibodies against that antigen. And then once we've got the antibodies, that makes it a lot easier to destroy the pathogen. This is the part that we have to accomplish to get acquired immunity. This is the part that takes time. This is the acquiring. We're not going to have antibodies in big numbers against specific antigens unless we've seen it before. Like my husband is test positive for TB exposure because he grew up in a country where it was more common. His body saw TB antigens. He made antibodies against it, fought it off before he got the disease. They're still around. I test negative because I never saw a TB antigen so far. So far. It takes time to acquire the antibodies. So what these graphs are showing, again, we got time across the bottom. And on the y-axis, it's telling us how many antibodies are in our blood plasma against that specific pathogen. So plasma antibody concentration. And the part where I'm saying we have to see the pathogen before we're ever going to make antibodies, that's the first exposure. If I've never been exposed to something, I'm not going to make antibodies against it. So if we get exposed at day 1, we will make a decent amount of antibodies, say by day 20. It's really slow. And these would protect us by helping destroy the pathogen, but it's slow. In between here, once we've made those antibodies, we also will make something called memory cells. These have a record of what we saw, and they know what antibodies they need to make, and they can make it on a moment's notice if we saw that again. So this is like, I don't know, if, like your grandpa, remembers somebody from 40 years ago that ticked him off, and he still remembers it, and he would still be ready to go today, right now, if he saw them again, because he remembers it. But he doesn't have a reason to remember them unless he saw them in the first place long ago. If they come around again, we're going to be ready. So here's the pathogen coming around again. We see it again some other time in the future. Then we make antibodies really fast because we have memory cells around to do it fast for us now. And we make really a lot of antibodies, so we've got more protection, and it happens a lot faster. Like it would only take, how much would that be? From this graph, it would only take 7 days to get the maximum number of antibodies we ever had the first time, and then we'd have more. This is what we want to happen. This is what being immune to something really is. It means that I can make antibodies against that fast to protect me because I saw it before. I have acquired immunity. So to do this, if we're going to acquire immunity, we have to start with usually seeing the antigens. That's the beginning. And when we have really accomplished acquiring immunity, we'll have these memory cells that can make more antibodies fast. So we want to have these memory cells that remember, oh yeah, we've seen that antigen before. We could make antibodies against it really fast and fight it off really fast this time. That's what true immunity really is. Questions so far? I know I'm going fast with this. So there's four ways that people in modern times can accomplish having this happen. How do we accomplish immunity these days? We've got vaccines. How else can people get immune to stuff?
Exposure.
You had it. Yeah, that's exposure. I literally had chicken pox as a child. How many of you had chicken pox? Still?
Oh.
Yeah. Now there's vaccines against it. Maybe people don't have to get chicken pox to become immune to it. These are the ways that we think about the most. We either get vaccinated against it, or we had the disease and we survived and now we've got immunity to it. And then there's two other ways. This next slide has a lot of words and it's got pictures of the 4 ways, but I want to go through what are these 4 ways that people can get to the point of having acquired immune antibodies to help protect them. And this process can be natural or artificial. And it also can be active or passive. So I'm going to go through the 4 ways. And each, it can be natural and active, or natural and passive, or it could be artificial and active, artificial and passive. So this material probably will become multiple choice or matching or something like that on the exam this week. So if we are having a natural version of acquired immunity, these are all ways of acquiring. If it's natural, that means that we made antibodies and we made memory cells ourselves. Ourselves. We made it ourselves. Which means that we did come in contact with the antigen ourselves. If it's artificial, what that means is we're using someone else's antibodies. We're using someone else's antibodies. And we didn't actually have to come in contact with that antigen ourselves. We're using somebody else's. So that's natural versus artificial. The other 2 sort of characteristics, whether it's active I've got these back. Okay, quickly. Switch this. This is active. This is passive. That's active and passive. So we actually made something ourselves versus we got it from someone else. Natural versus artificial. If it's artificial, that required some kind of medical process. You had to have a medical professional in some way help you with that process. If it's natural, that's something that could happen on a desert island. Or it could happen, in an uncontacted tribe that's never seen modern society. It doesn't require any intervention. So those are the definitions. So you can take any combination, those two together, those two together, those two or those two, and you can come up with these combined situations like I've got on the screen. So I'm not going to write extra notes on these, but talk about how those relate to this. And we'll start with the ones that we're most familiar with. Okay, say that you get a disease, you become infected with a pathogen, it makes you sick, and you survive it. You survive it, and you make memory cells of your own. It's active because your body did the making. Why is it natural? That could happen without you ever going to the doctor. The doctor could help you survive it, but there was no medical intervention to help you make antibodies. That's natural, active. So you caught the disease, you survived it, you made your own antibodies. Okay, here's another one that's pretty natural. And this one's focused on the baby, not the mom. So the baby, by breastfeeding, is getting antibodies from the mom, but the baby did not encounter the disease, and the baby did not make them. It's just ingesting them. That's natural, that's passive. The baby didn't make it. This doesn't require medical intervention. So, both of those could happen on a desert island, no doctors, nurse around to help. These that are artificial, the artificial require modern medicine. Vaccination is artificial. Nobody accidentally has that happen to them. It's on purpose. It requires medical intervention. It's artificial. But when you get vaccinated, you make the antibodies. So if you just went and got a flu shot last week, and you ask them, how long will it take before it works? That's how long. Because you're making your own antibodies against it. And then in the future, if you get subsequently exposed, you'll make more. But it was an artificial situation from the start. That's active and artificial. This is the one that, like, we're not used to thinking about. And so what this is a picture of is this girl. What's this thing? Can you tell? She's got an IV bag. It's connected to her. And what's in here are somebody else's purified antibodies that were taken out of them, and we're giving it to her artificially. She didn't make them. This would not happen naturally. It's requiring an IV bag. It required that we get these out of a person, purify them, give it to her. So it's artificial, but it's passive because she didn't make those antibodies. She's just getting them. She's getting immunity from another person. Questions about this? There's 4 types. Each type is either active or passive. Each type is either natural or artificial. What's vaccination?
Artificial.
It's artificial.
Passive.
It's active. It's active. Because you do make the antibodies yourself. What's getting a disease and surviving?
Natural.
That's natural, and it's active. What's the IV infusion thing?
Artificial. Passive.
It's artificial for sure. It's passive, because you're just getting it from someone else. And then baby's breastfeeding, that's natural for sure. It's passive. The baby's just drinking it in, not making its own immunity. It's too little. It doesn't have the capability yet. Oh, there's a quiz. Okay. So that's the end of the new material. Everything going back to the start of innate immunity, that's going to be multiple choice material on the test. It doesn't mean it's not important, it's just there's not a big conceptual question. Kyler, if you would push the but we can have a little bit of review time.